Hi guys, for quite some time I was thinking that using diffusion for text generation would be quite cool instead of autoregressive method, especially for local people. And today we'll look about what is diffusion in text models. We'll check the new Gemma diffusion model. We'll also deploy it using vLLM with containers on RTX 6000 Pro, and we'll see how to achieve 6 times more speed than using the normal model, just like this. Here on the left, we have Gemma4 26 billion with 4 billion active parameters in NVFP4. And as you can see, we have 159 on average. And on the right, we have the diffusion version in the same format in NVFP4. And as we can see, on average, we have 929 tokens. And we can see now at the top that the speedup is calculated here, and it oscillates depending on the usage. So right now it's 568, but depending then on the task and everything, it will oscillate between 5, 6, sometimes 7, depending on the prompt. So now let's jump into the explanation of how all of this works. So let's start with the normal LLM setup. Most language models generate text one token at a time. The model reads the prompt, predicts the next token, adds that token to the context, and then runs again to predict the next one. This is autoregressive decoding. Now, this sounds a bit inefficient, but in the cloud it works very well. Why? Because of batching. Imagine a server, ChatGPT style, like with 1,000 users. We have user 1, 2, 3, 1,000, and they all send requests in the same time. These all requests goes into one batch, and then we load model weights from memory once, and then we compute 1,000 next tokens in parallel. So by doing this, we'll use the GPU lanes efficiently. So the full GPU will be used to compute all these tokens. But if we apply the same to a local AI when we have one user, to the batch we'll only send one token. Why? Because we usually send one request, maybe 2, 3 requests if you do parallel agent tasks, but you send one request with a prompt and then you wait, you refine, and you send it again. So in this case, we will do the exact same thing, but we'll only compute one token at a time. So if you look at the timeline, when we wait for the request, we load the model, do math, load, do math, and here we have pauses. So the main message is that the batching fixes throughput, but it's not a good solution for single user latency. And this is where Diffusion Gemma could become interesting. So this slide shows the trade-off. On the left, we have a cloud autoregressive inference. This is the happy case for normal LLMs because we have many users that share one GPU, and then the inference provider is becoming rich. So the model generates one token per user, but because we have many users, we batch it together, so we have full utilization of the GPU. In the middle, we have local autoregressive inference. This is a typewriter problem. We have one user, one request, one token per pass. The model writes one token, waits, writes one token, waits, and writes next one and wait. So the GPU timeline has these small bursts of compute with waiting in between, but the utilization is still low. So this is not because the GPU is not managing well, it's because we are not giving it enough work, because we are typically having a lot of compute when we are the local users, that we are not sending constantly prompts every time we need to think, write a new one, and so on. And on the right, Diffusion Gemma tries something different. Instead of generating one token at a time, it will work on blocks of tokens, which are named a canvas. So in Diffusion Gemma, the canvas is 256 token. But this is important. It does not mean the model writes 256 perfect tokens in one pass. This is not how diffusion works. The better way to think about this is the model creates a rough block, revises that block through multiple passes. Before we talk about Diffusion Gemma, let's quickly remember how diffusion in images works. On the left, we have noisy image. Noisy image is the input that gets encoded into a noisy tensor through image encoder. Noisy tensor is a numerical representation of all of that chaos in the image. On the right, we have the text prompt, flamingo on the beach, and it gets tokenized through token embedding layer, embedded and run through the text encoder that extract what this word actually means semantically. Both streams then are fed into the denoiser here and then here. This is where the magic happens. The encoder output acts as a compass. It tells the denoiser what the final image should look like. So we get information here to the denoiser. And at each step, it removes the noise from this that doesn't belong to a flamingo on the beach prompt and keep the noise that could become one. This loop repeats each pass. It gets a little cleaner without the encoder providing that guiding signal. The denoiser would have no idea what to school from the random noise. It would just produce, well, random noise. Once enough denoising steps are done, the resulting tensor goes through the image decoder, which translates the clean latent representation back into actual pixel space. And that's our output, an image of flamingo on the beach. So for images, noise is easy to imagine. A pixel can become slightly more red, slightly more blue, or slightly more random. But text is different. A token is not a pixel. How do you make the word LLM slightly less LLM? There is no smooth halfway point between LLM and flamingo. So text diffusion needs a different kind of noise. Instead of corrupting pixels, we corrupt token positions. That means a correct word can be replaced by a random wrong word. Now the model job is find which tokens are wrong, keep the tokens that look right, and fix the tokens that do not fit. Now let's look at the top part first. This is called mask diffusion. And the idea is simple. We start with a sentence where every position is hidden, and how we hide it? We use mask. So here every position is hidden, and this is step T0, and we name it initial noisy canvas. And that means that I know there should be a word here, but I don't know which word yet. So the model starts filling in the blanks. Maybe it's very confident that the second position should be LLM. So we choose it, and we don't choose them because we think that there is low probability there. So we keep mask here. So we fill that in. Then we become confident with this, that at should be here, and then with this we are confident that pix should be here, and then all, and then by using all of this we choose words once. So after several steps, all masks are gone, and the final sentence becomes the LLM picks words all at once. So mask diffusion is like worksheet. There are blanks, the model fill in the blanks step by step. The useful part is that the model does not need to decide every word at once. It can fill the easiest positions first, then use those words as clues for the harder positions. But there is weakness. Once the model fills a blank, the choice is basically not reversible. So if we choose this, we can't reverse it. If we choose LLM here, we can't reverse it. We can't go back from T3 to T2 or T2 to T1. This is similar to autoregressive generation. And once a normal LLM writes a token, it moves on, it never comes back. So mask diffusion is not exactly the same as normal LLMs that are autoregressive, but it has similar choices that we can't fix the early choices. Now let's look at this. This is uniform state diffusion. Here the noisy canvas does not start with mask. It starts with random tokens. So instead of mask, like here, we have random tokens, high, test, dog, tiny, and flamingo ones. So it doesn't make sense, yeah? But that's the point. The model is not filling blanks anymore. It's repairing a corrupted draft. So every position already has a token. And the question is, does this token belong here? So at each step, the model looks at the full canvas and gives confidence score for each position. If a token looks good, it can stay. So as we can see here, we do a few passes, and just at T4, we choose I, Apple, token. And as we can see, here we have LLM, but with next step, it becomes more sure that it should be at the second position. So we say that the token become more stable. But if a token looks wrong, the model does not have to keep it. It can renoise that position. That means the weak tokens get replaced with another random tokens, and the model tries again on the next pass. This is the key difference. So as we can see, we have pick here, and then we choose that pix is better and closer to feed it. We have word, and then we choose words here. That means the weak tokens get replaced with another random tokens, and the model tries again on the next pass. So as we can see here, we have pick chosen here, but we then changed it to picks. We were not sure about a word, but because we have already this, then we choose words, and then there was token, but after 2 steps, we choose it to all after knowing all of this. So this is the key difference. Mask diffusion says this position is blank, fill it. Uniform state diffusion says the position has a word, but the word might be wrong, so we keep checking it. So a model can self-correct. A token that looked good early on can become less likely later on once the rest of the sentence changes. And a token that was random noise can gradually turn into the right word. This is why uniform state diffusion fits Diffusion Gemma, because Diffusion Gemma is not trying to fill a worksheet, it's trying to clean a noisy canvas, and the canvas starts messy. So the confident token stays, weak tokens get renoised. Then the important tokens help fix the rest, and after several passes, the draft becomes coherent. And that's a big advantage in LLMs. So you can notice that even though Diffusion Gemma works on many token positions in parallel, not every position is equally easy. Look at this example. The core idea behind Diffusion Gemma is, even though Diffusion Gemma works on many tokens positions in parallel, the first few tokens are easier. The core idea is very natural start, but later tokens are harder. Why? Because later tokens needs to fit the full meaning of the sentence that depend on topic, the structure, and where the explanation is going. So early positions often become clear very quickly, and later positions need more refinement. This is why Diffusion Gemma does not just predict the whole canvas at once and stop. One pass give a rough draft, another pass improve it, then the clearer token help the uncertain token, then the whole sentence becomes more coherent. So the key point is Diffusion Gemma works in parallel, but it's not one-shot generation. Parallel mean it can work on many token positions during the same step. Iterative means it improves those positions over several steps. That is the difference. It's not typing one word at a time, it's polishing a whole draft at a time. Now let's quickly look how all of this look in the Gemma architecture. So Diffusion Gemma uses one Gemma style model, but it uses it in 2 different ways. Think of it like a person doing 2 jobs. First, the model acts like a reader. It reads the user's prompt and builds an understanding of what the answer should be about. For example, the prompt might be the LLM picks. At this stage, the model is not writing the answer yet. It is only understanding the instruction. This is the prompt side, yeah? And it gives the model the context and then code it so it would be understood by the denoiser. Now comes the second job. The model acts like an editor. Instead of writing one token at a time, it starts with a noisy block of token position. This block is called, as we said before, noisy canvas or just canvas. So at first the canvas is, as we see, messy, fancy, test high. This doesn't make sense. So we try to clean as many positions at the same time. And the prompt is the instruction to help us clean it. And the canvas is the draft. And the model uses the instructions to improve the draft. But the important difference is in attention. A normal autoregressive model writes left to right. So token 10 only depends on token before it. So from 1 to 9. But it cannot use token 11, yeah? Because token 11 will be generated in next step. And so it doesn't exist. But Diffusion Gemma already compute full canvas, even though some of the words are wrong, like here. So will it refine is the token position can look at each other. So if token 1, it can look at the last token, and token 2 can look at token here. This is simplification of the block that we mentioned before, like the 256 block in the canvas. And this is called bidirectional attention. This is why this architecture work quite well, because it's like editor looking at the full paragraph and improving over and over again. And as we can see, after some step, we have all words, Gemma once. So we do it multiple times, yeah? This is multiple steps. Step 1, step 2, we choose, for example, words, and then all, and this change to Gemma, and where change to once. Now we can compare the two methods directly, yeah? So autoregression writes left to right, the text diffusion drafts the full canvas and refine it. Yeah, in parallel we can see it here, and this is autoregression. So now let's summarize the differences. Yeah, the token generation, one at a time. We have full canvas of tokens at once. Steps, we have one step for each token, and here we have one step for multiple tokens. The generation order, left to right. Here we have all positions in parallel. And the starting point is the empty sequence, but here we have random tokens sampled from the vocabulary. And if you look at error correction, this is static. We can't come back and change the tokens that we already choose, but here it's dynamic. We can revise any canvas position. So the bottleneck for this, as we said, is memory bound, and for it, it's compute bound. So the true output focus for autoregression is for high multi-user throughput, and the text diffusion is for ultra-low single-user latency. So as we can see, the big idea was that autoregression model will scale by batching many users, and diffusion will try to use all the possible compute for just one user. Before we jump to demo, there is one term in the model name that we showed earlier that can look intimidating: NVFP4. The simple version is this. NVFP4 is a more compact way to store the model's numbers. A model is basically a huge collection of numbers. Those numbers are the weights and activations the GPU has to read, move, and calculate with. So the size of each number matters. With BF16, each value uses 16 bits. This is like putting every number in a bigger box. Bigger box takes more space, and more space means more data has to move through GPU memory. NVFP4 uses much smaller 4-bit values. This is like putting the numbers in smaller boxes, so the GPU has less data to move. But there is important catch. NVFP4 is not just make the numbers tiny and hope it works. It also stores scale information. Think of the 4-bit value as the rough shape of the number. The scale factor tells the model how big or small that number should be in its local group. It scales data and keeps the map, so there is less data to move. So the scale is like little map that helps the compressed numbers still point to useful values. This is why this is not free magic. Quantization is a compression. It can make the model smaller and faster, especially when memory movement is bottleneck, but it's still only an approximation. So the goal is move less data, reduce memory pressure, speed up the inference to print more bugs, and keep the answer quality close enough. Here we can see regarding NVFP4 that there is minimal reduction in the accuracy. We have FP8 baseline and NVFP4. And as you can see, we have benchmarks on DeepSeek R1, and we can see that there is a bit lower scores in some of these tests. So this is also something to take into account. Now let's see with visualization to better understand why the scale matters. When we compress the model numbers to 4 bits, the 4-bit number alone is not enough. This is the original value. We also need a scale. The 4-bit number gives the raw value that we describe. So the scale needs to tell us how big or small that value should be. It's like using a ruler with only big tick marks, so some values get rounded too far away. The bottom example uses a more flexible scale. It's like using a ruler with smaller tick marks, so the compressed values can stay closer to original values. This is the idea behind NVFP4. NVFP4 uses 4-bit values, and it uses A4 and 3 scale information to help those small values stay useful. I will put the reference of the blog so you can understand what is EAMO, which is this, and E4M3, which is the fractional scale. In simplification, these are the original values in 4-bit, and as we can see, they are separated from these values. They are not exactly where they should be, but after applying scale, we then have these values in the same line as the original ones. So as you can see, it's not exactly the same, but it's closer than with just power of the 2 scale, which is E8M0. And also what you can see is that we have the average error here, MSE, which is 0.72, And after we do scale, it's 0.08. So this is the test that we're running at the beginning. This is 30,000 of context. And as we can see on the left, we have the basic Gemma4, 26 billion, 4 billion active parameters in NVFP4. And on the right, we have the Diffusion Gemma. I changed the prompt, so it's something a bit different or complicated. And here we have the measure of the speed by the average speed of tokens. And as we can see, it's already 6.75 times faster. So it will run for 10 runs, because that's how I define it. And we'll see what will be the summary and the total speeds at the end, because it prints table. And also after this, we'll talk a bit about the quality of the output, yeah, because the speed increase is quite big. So there should be a catch, yeah. We are back. And as we can see, this is the summary. I put it here so it's more visible. For Gemma4 27 billion, we have 157 tokens. And for the diffusion one, we have 1062. So as we can see, the speedup is 6.73x times. So now let's talk about what this scores means and if there is any drawbacks. And before we jump to actually this, I want to show quick visualization that Unsloth prepare. So here we have the prompt, and the goal is to see how the canvas change. So we'll see that there are some output tokens produced, but they will be changed in real time when we run it. So as we can see, it's pretty fast, but we can notice that sometimes the value changed after being printed, yeah? For example, here, and so on. So this is recording from Unsloth, and there is special flag to have a visualization of tokens. And as you can see the token increase here, and it produces a Flappy Bird game. This is something interesting also to see how, after all of this explanation, this actually works. Now the question is, what is the cost? And as we can see, we have here graph from Google, intelligence versus latency for one H100 with FP8, and this is, I think, batch size of 1. So as we can see, we have the Gemma4 31 billion with MTP, and we see the output per second. So also something you could notice, smaller model or MOE models have better output speed, which is expected by the architecture. And here we can see the Diffusion Gemma, and as we can see, it has the highest amount of tokens, but we have a slight drop in intelligence. But this is still quite a good score, and it's average GPQA Diamond LCB V6, so that's the benchmark they choose. And here we can look at the Diffusion Gemma score versus the standard one for various benchmarks, and also the output speed that we mentioned before. So as we can see, we have a slight drop in the intelligence. And if you want to have high speed for single user, this is also something quite interesting. So as we can see here, Unsloth fine-tuned the model to solve Sudoku. And Sudoku is a task that autoregressive models struggle with because each token depends on future token, yeah? And in Sudoku, if you solve it yourself, you sometimes change numbers because then you see that with one row or column, they were not fitting perfectly. And here we can see there is a base Diffusion Gemma versus fine-tune one. And the fine-tune one is Diffusion Gemma. As we can see, it solved Sudoku super quickly because that's like a task that diffusion makes sense because it takes the bidirectional attention context to easily solve it. So there could be very specific tasks that it could be quite beneficial, yeah? And also fine-tuning the model typically increase the accuracy for specific tasks. So if we have a good data set, then we can fine-tune the model and enjoy this high speed. Or if we have a lot of compute, then also this could be very important here, because on autoregressive task, we are more memory bound than compute bound. And if you look here, we can see now that we have prompt that we want to create a legendary fantasy sword with a glowing blue gemstone and crossguard. And as we can see on the left, the tokens change sometimes. On the right, we have live 3D scene. So this is visualization how diffusion works. And here, if we want to change something, we can see that it will change. So to summarize, I think this is a good summarization of Gemma. It's very fast at math, but it's not always right, but it's always fast. And regarding the hardware, here you can see I use 14.1 CUDA version with 6000 Pro. This is my driver version. My CPU is AMD Ryzen 9 9950X 16-core processor with 32 CPUs. So this is the setup that I run it on. Here we can see the repo. So as always, there is download model script, but you can also do it normally through the flag. I just use it because my internet is quite bad, and there's PyProject on, so you can just do UV-sync to download all of this, and then you will have the app with visualization to run 10 tests side by side. And there is also leaderboard that I use when I, for example, couldn't fit the model, so then you run model one by one, and then it saves the score, so you can track the score. Yeah, I only use this because it looks better. And then there is Docker Compose with all set up to run it. It, at the time of making this video, was only supported on vLLM, but I see that llama.cpp PR is getting merged, so it should be also available for llama.cpp. And yeah, if you like this video, you could also check my other videos, yeah, when we tested MTP. As you can see, I'm also preparing other Dockers with QAT models from Gemma, because this model is Apache 2 and there is more models coming. There is 12 billion version and so on. So I'm still in the middle of testing them. So yeah, if you like it, guys, like and subscribe, and see you